Hello, am I audible?
Yes.
Okay, let's wait for a couple of minutes. After that, I will start. Okay, so let's start. So, hello everyone. Good evening. So last week,
Good evening.
yes. So last week I
Sir, good evening, sir.
yes. So good evening to all of you. So last week I discussed about design of shallow foundations. I solved some problems regarding design of shallow foundations. I hope you have gone through the uh, last session. The recording is also available on the site and YouTube also. So today I will be talking about pile foundations under compressive load. Okay. So first of all, let me just uh, say something about pile foundations. What is a pile foundations? Just a brief, and how does a pile foundation transfer the superstructural load? Okay, so first I will just talk about that a brief, and after that I will solve some problems. So let me share my screen. Please let me know if you can see my screen or not.
Screen is visible.
Okay. So today is our sixth session, and today I'll be talking about pile foundation. So, what is a pile foundation actually? So, pile foundation generally, suppose you have a very weak top layer whose bearing capacity is very low, and if you build a shallow foundation over a weak topsoil stratum, then you may face bearing capacity failure or differential settlement. Okay, so in that case, what we do is that we construct pile foundations. So generally what pile foundations do is that it carries superstructural load and it transfers that load uh, to a hard stratum or maybe to a suitable strong stratum through skin friction and end bearing, or through skin friction or end bearing, or combined action of both. Okay, so let me just first draw that, and after that I will explain. So suppose you have a weak layer like this. This is a suppose this is a weak layer, weak topsoil stratum, and you have high superstructural load coming from the structures. So if you just construct a shallow foundation over here, here maybe so there could be a bearing capacity failure, maybe geometry failure like that. There will bulging, all sort of that. Okay, maybe differential settlement. Maybe the shallow foundation may tilt also like this. Okay, so in order to eradicate such problems, we construct pile foundations. So what pile foundations do is that so we generally construct a pile foundation like this. Load is coming from above, and suppose this one could be a rock. Suppose this layer is a bedrock. Okay, suppose this pile is resting on the bedrock. So what is happening over here is that the superstructural load coming from the top is transferring to the bedrock through the tip of the pile caps. This is the tip. This is the tip of the pile cap, and this one is the head of the pile cap. Okay, head is above and tip is below. So load is acting through the pile, and it is transferring to the bedrock. It is transferring to the bedrock through the pile tip. Okay, and this is the end bearing pile, because the complete load is being transferred to the bedrock via end bearing. Okay, this is it is transferring through the tip to the bedrock. Okay, and no friction is involved. Another case is that there is another case where suppose this is a weak layer, and suppose bedrock is at a very depth. Okay, suppose at a great depth, bedrock is at a great depth, but this stratum is comparatively good stratum, hard stratum. Suppose stiff clay or maybe stiff sand. So suppose stiff clay or dense sand. So what will happen is that there will be skin friction along the length of the pile. Okay, suppose you are applying load like this, and all the load will be carried by the skin friction along the length of the pile. So here no
Sir,
yes, tell. Hello. Okay, so
sir, voice is not coming clearly.
voice is not coming clearly. Okay, let me just check it once.
Yes, sir.
Okay, wait a minute. Is it working properly? Can you hear my voice clearly now?
It's okay, sir. Sometimes it is breaking.
Oh, sometime it is breaking, right? But is it clear now?
Yes.
Uh,
Ah,
uh,
okay, sir.
okay, so if it is not clear, please let me know so that I will try another setting. Is it clear now?
Ah,
Is
it's clear.
okay, okay. So as I was saying, so suppose this layer is stiff and load is acting, structural load is acting on top of the pile, on the pile head, and all the load is being carried through the length of the pile via skin friction. Okay, here no end bearing is involved. But in certain cases, what happens is that in these are totally ideal cases, but generally what happens is that combined action takes place. Here this is a hard stratum. Here this hard stratum will also provide end bearing. Actually, like this. Suppose this is your weak layer, and superstructural load is acting on top of the pile head, and along the length, soil is providing skin friction. Along the length of the pile, soil is providing skin friction, and since this is the hard stratum, end bearing will also be involved. Load will also be transferred to the soil underneath the pile, via skin friction, via end bearing resistance. Okay, so if we formulate the total bearing capacity of a pile, we will write like this: QU, we represent ultimate bearing capacity of a pile using QU. This QU is equal to QPU. This one is the end bearing resistance, total end bearing resistance, plus QF. This QF is the total skin friction resistance. Skin friction resistance. So this one is QPU, total end bearing resistance. This QF is the total skin friction resistance. In case of end bearing pile, in case of end bearing pile, this term, this QPU term is much greater than QF. Okay, because all the load is being carried by end bearing, that is the bedrock or maybe hard stratum. Okay, all the load is being carried by hard stratum, is being transferred to the hard stratum. No skin friction is involved, or very less skin friction is involved. So end bearing resistance is much higher in case of end bearing pile. And in case of floating or friction pile, what is happening? It is being carried by, all the load is being transferred to the surrounding soil via skin friction. So in case of friction pile, this QF, that is the total skin friction resistance, is much greater than the end bearing resistance. Okay, so Q is equal to QPU plus QF, that is total end bearing resistance and total skin friction resistance. So this QPU term, it can be again we can write it like, since it is being since QPU, that is the total end bearing resistance, involves the tip of the pile. That means the load is transferring to the base, to the bedrock or maybe hard stratum through the tip of the pile. So so we can write it like this: this QPU can be written as QPU into AB. This QPU, this one is the total end bearing resistance, this one is the unit end bearing resistance. Okay, this small QPU, this one is capital QPU, this one is small QPU. This is unit end bearing resistance. So this is end bearing resistance. The unit is generally kilonewton per meter square, and this one is the area of the base of the pile. Okay, area of the base of the pile. So area of the base of the pile.
Progression is not showing.
Hello.
Sir, progression is not showing. This subsequent what you write in the screen, it is not appearing.
Oh, you can. Oh, wait a minute. Oh, ho, ho.
Yes, yes. Now it's okay.
Oh, now it's okay.
Now it's okay.
Okay, okay, fine. So as I was saying, Q, the total ultimate bearing capacity of the pile, is equal to the end bearing resistance, total end bearing resistance, plus the total screen friction resistance. Okay, so total end bearing resistance can be written as unit end bearing resistance multiplied by the area of the base of the pile. Since the load is being transferred to the hard stratum or bedrock via through the tip of the pile. So this QPU, the small QPU, is the unit end bearing resistance, and AB is the area of the base of the pile. If we multiply these two, we will get the total end bearing resistance. The total end bearing resistance, that is capital QPU, the unit is generally kilonewton, and small QPU, the unit is kilonewton per meter square, and AB is meter square, so kilonewton meter square into meter square is kilonewton. So QPU, the unit of QPU is kilonewton. And in case of QF also, that is the total screen friction resistance, it can also be written like it can also be written as unit screen friction resistance, the Fs. Small fs is the unit screen friction resistance. So unit screen friction resistance multiplied by the surface area of the pile. Okay, surface area of the pile. This one is the area of the tip of the pile, area of the pile base. If we know the diameter, we can just find out the area of the pile base. And Q and this AS. What is AS? AS is the surface area of the pile, which can also be found out if we know the perimeter of the pile. If we know the perimeter of the pile and if we multiply it with the length of the pile, we will get the surface area of the pile. Okay, that is, suppose if it is a circular pile having diameter d, so what will be the perimeter? It is pi d, and if we know the length, if that means pi dl, so perimeter into length, if we just multiply it with the length, perimeter and length, we will get the surface area of the pile. Okay, so that is AS. Since the skin friction is acting along the surface of the pile, so in that case we will consider AS. And the unit is also same like that, so like the end bearing resistance. So Fs, the small fs, the unit skin friction resistance, the unit will be is in kilonewton meter square, kilonewton per meter square, and capital As, that is the surface area, is also is in meter square. So kilonewton per meter square into meter square will give kilonewton. So capital QF, this one is the total screen friction resistance acting along the surface of the pipe. The unit of QF will be kilonewton. So I hope you have all understood this. If you have any doubt in this concept, please let me know. This one is very basic. I am just
Yes, it's okay, sir.
okay. So let me just talk about end bearing resistance a bit. So we know that we know the bearing capacity equation of shallow foundation. Tarzag is bearing capacity. So what is the bearing capacity formula? It is CNC plus sigma dash, that is the overburden pressure at foundation depth, NQ, that is the surcharge bearing capacity factor, NC is the cohesion bearing capacity factor, plus 0.5 gamma B and gamma. This is the bearing capacity equation for a strip footing. Okay, so this is the bearing capacity equation for a strip footing. So if we apply this to a pile, suppose if we apply this to a pile, suppose this one is the, suppose we consider this to be the bearing capacity of a pile, okay? We are not considering screen friction, okay? We are only consider end bearing, since this tip is also resting on a soil. You see, this is a soil layer and this tip is in contact with the soil. So we can say this has some bearing or end bearing or maybe bearing capacity. So bearing capacity equation can also be, yeah, we can also incorporate this, you can also incorporate and use this bearing capacity equation for shallow foundation in this case also, since because the tip of this tip of the pile is also contact with the soil. So you can find out the bearing capacity using this equation. So here one thing we must remember, since this pile is very slender and the depth is very long, depth is very large, so in that case overburden pressure at the pile tip will be very large. So this term q dash nq will be very larger than 0.5 gamma bn gamma. Then this term, okay, this will be much greater than this term, since overburden pressure at pile depth will be very large. So we can ignore this term, okay, we can ignore this term since because this will be very small term. So bearing capacity equation for pile we can write it like this. So CNC plus sigma dash NQ. Okay, we can ignore the third term. So now what happens is that for granular soil, C will be equal to 0. That means this term will be equal to 0. So the bearing capacity will be sigma dash NQ. Okay, and for cohesive soil, this C will be present, the C will be present, but what will happen is that C will be present, but phi will be equal to 0, right? For cohesive cell, phi will be equal to 0. So if you can remember in shallow foundations, in shallow foundations lectures, if phi is equal to 0, NQ is also equal to 0, right? If phi was 0, NQ was also 0 in shallow foundations chapters, because this one depends upon the phi, and if phi is 0, this NQ, the last term is all, the second term is also 0, okay, since this depends upon phi. If phi is equal to 0, this term is also 0. So in case of cohesive soil, this QPU is equal to CNC only, okay. So why I am writing all these things, you will understand. So let me write down the bearing capacity equation once again for pile. So QU equal to QPU plus QF. Okay. So as I have written earlier over here, so QU equal to QPU plus QF, and QPU equal to small QPU, that is the unit end bearing resistance, and multiplied by the base of the area of the area of the base of the pile, plus QF, that means Fs, that is the unit skin friction, and As, that is the surface area of the pile. Okay, let me just write it down once again over here. Small QPU into AB plus Fs As. You have all understood this equation. So for cohesive soil, Fs, that is the skin friction, will be alpha. Alpha is the adhesion factor. Okay, adhesion factor means, suppose C, what is C? C is the cohesion between soil particles. Okay, and the cohesion between, suppose we are inserting a pile, we are constructing a pile. So the cohesion between the soil part at the interface between the soil and the pile. Okay, so the cohesion at the interface. So since what is cohesion? Cohesion is the force of attraction between two similar particles. So we can say cohesion presents in soil particles because both the particles are similar forces of attraction. But if we construct a pile, since pile is of different material, so forces of attraction between soil and particles. soil and the pile, the material of the pile. The forces of attraction between the soil particles and the pile that we are constructing, the force of attraction, we call it adhesion, not cohesion. Okay, and it is generally lower than that of the cohesion. That is, cohesion is the force of attraction between like particles, like soil particles. So alpha is a factor, adhesion factor, multiplied by C. What is C? C is the cohesion along the length of the pipe, along the soil, which is along the length of the pipe. Okay. So alpha into C. This is Fs, that is the unit screen friction resistance. And QPU, that is the unit end bearing resistance. What is that? It is this. C. For cohesive unit end bearing resistance is CNC. Okay, it is CNC, and NC is considered to be 9 in this case. So it is 9C, and this C is the C at the base, at the C of the soil, which is at the base, underneath the base of the pile. Okay, underneath the soil, underneath the pile head. So what is it? So let me just draw it and explain it once again. So this C dash is along this. Okay, C dash is along this, is over here, the cohesion of this portion along the length of the pile, and alpha C will provide the adhesion at this, at the contact between the soil particle, at the interface between soil and the pile. Alpha C will provide adhesion between soil and the pile. Okay, and this C is the cohesion of this portion. Okay, of this portion beneath the pile head, pile tip. Cohesion, cohesion of soil of this part underneath the pile tip. So I hope you have understood this. This is for the cohesive soil, 9C and alpha C. Alpha C is the unit screen friction resistance, and QPU is the unit end bearing resistance. And for cohesionless soil, Fs, that is the unit screen friction resistance, will be K, that is the lateral earth pressure coefficient, multiplied by QAV dash. What is QAV dash? It is the overburden pressure, average overburden pressure, multiplied by tan delta. What is delta? So we know phi. What is phi? Phi is the angle of shearing resistance or angle of friction. So frictional angle between the soil particles. So what is delta actually? So what is delta? So this delta is the angle of shearing resistance between the soil particles and the pile. Okay. Suppose this is a pile. You know the phi value of the soil layer, but phi value at this contact, okay, at the interface between the soil and the pile, there will be friction, right, between the soil particles and the uh, pile surface. Between the soil surface and the pile surface, there will be friction. So that frictional angle is delta, okay, which is also a factor of phi. So generally delta is some factor, suppose a factor, suppose A, multiplied by phi. Phi is the frictional angle of soil. So this is so now QPU is the end bearing resistance, unit end bearing resistance, which is equal to, see, I have written it over here, QPU. This is the unit end bearing resistance, which I have derived from the bearing capacity equation of shallow foundation, which is, it is QPU equal to sigma dash NQ. So you can write it for cohesionless soil. This is also for cohesionless soil, granulous soil. So that is sigma dash into NQ. So QPU can also be written as sigma dash into NQ. Sigma dash is the effective overburden pressure, and NQ is the surcharge bearing capacity factor. Okay. So if you have any problem, please let me know. if you have any doubts.
So that please that nine how it came nine number.
Oh,
CNC is equal to 9C.
C and this one. Actually, this is these have come from an empirical equation. This we must consider it is equal to 9 for every case. Okay, for cohesive soil, this NC is equal to 9. We must use this to find the unit end bearing resistance. This one
For
is
cohesive soil. For
for
cohesive soil.
cohesive soil. QPU is equal
Okay,
to
okay.
CNC and NC is equal to 9. Okay, just
Okay, okay, okay. Thank you.
and for cohesionless soil it is sigma dash NQ. See, I have written it over here. Same thing. This CNC here NC is equal to 9 and QPU is equal to sigma dash NQ, where sigma dash is the effective overburden pressure. And we must also note that this QPU should not be greater than 11,000 kilonewton per meter square. Okay, so I
Which
hope
one, sir? 11? What do you
this
QPU is equal to
uh,
sigma dash and Q.
this QPU is equal to sigma dash NQ, and this QPU, after finding out this QPU, we must ensure that it must be lesser than 11,000 kilonewton. Okay.
Acha, acha, okay.
So suppose we are calculating QPU, and if we get the value like 15,000 kilonewton per meter square, okay, we must consider 11,000 at that time. Okay. So I hope you have all understood. So
So why it is 11,000, sir?
because it is a limit, because if we increase, suppose we are getting 15,000 somehow, and that means what, that means the bearing capacity of the pile will be very high and it will be very conservative. So 11,000 is a limit which the researchers have set. The researchers have set such a unit in order to make it much safer. Okay, because
Acha, acha.
we can consider lesser, right? If the bearing capacity is much higher, we can, it is better to consider less, right?
QPU, okay.
It is better to consider
Okay,
lesser
okay, sir.
value.
Okay.
Okay. So now let us come to the first question. So what is the first question? 15-meter long, 300 diameter pile. Let me just write everything down. 15-meter long pile, that is length of the pile is 15 meter, diameter is diameter is 300 is driven in a uniform deposit of sand phi, whose phi is 40 degrees. The water table is at a depth of 2 meter below the ground level. The water table is at a depth of 2 meter below the ground level. The unit weight of the sand above and below the water table is 18 and 20 kilonewton per meter respectively. Let me just draw it first. Suppose you have a pile like this, a 15-meter long pile. It is driven in a uniform sand having phi equal to 40 degree. Suppose the phi of this layer is 40 degrees. The water table is at a depth of 2 meter below the ground level. Suppose this depth is 2 meter and water table is over here. The unit weight of sand above and below the water table is 18 and 20 kilonewton per meter cube. So unit weight of sand of this part is 18 kilonewton per meter cube, and unit weight of this part below the water table is 20 kilonewton per meter cube. Using K is equal to 2, K is the lateral earth pressure coefficient. Let me write it down. K is equal to 2, and this is delta, that is the angle of shear, frictional angle between the soil and the pile. So delta is equal to 3/4 of pi, pi, that is the frictional angle. NQ, that is the surcharge bearing capacity factor, it is 135. So we have been asked to find out the ultimate load carrying capacity of the pile. Consider the critical depth concept. LC is equal to 20D for dense sand, and unit weight of water is 10 kilonewton per meter cube. So what is critical depth? So critical depth is such a depth that below that depth the skin friction remains constant. It is also considered while designing the pile. Below a certain depth, that is 15D for loose sand and 20D for dense sand, the skin friction is constant. In this numerical, skin friction is constant. So what is skin friction? I have written it over here. For cohesionless soil, this is the unit skin friction, K into sigma dash AV, that is the surcharge overburden pressure, and tan delta is the angle of friction angle between the soil and the pile. So after a certain depth, this Fs is constant. In other words, it is considered that below the critical below the critical depth, the overburden pressure is constant. It is considered while solving such sums. See, this Fs depends upon this, the overburden pressure, average overburden pressure. So it is considered that below a certain depth, this Fs is constant. That means this sigma dash Av is constant, because you see all are constant. This tan delta is constant, K is constant. So this will also be constant, right? K is constant for a soil. This delta is also constant, and delta is also constant. So sigma dash AV, it is considered that it is constant along the depth of the soil below the critical depth. So if all these are constant, Fs is also be constant. Okay, Fs will also be constant. So below the critical depth, Fs is constant. So what is the critical depth over here? Critical depth is LC is equal to 20D. So let me draw it once. So let me just find out the overburden pressure along the depth. So first of all, let me find out the critical depth. What is critical depth? It is 20D. So critical depth is equal to 20D, which means what is the diameter of the pile? Diameter is 300 millimeter into 0.3 meter, which is equal to 6 meter. So that means here is the pile, here is the pile, below 2 meter there is a water table, the length of the pile is 15 meter. So critical depth is 6 meters. Suppose up to this is the critical depth. Critical depth. Okay. So let me just find out the overburden pressure along the depth of the pile. So what is the overburden pressure starting from here till at the 2 meter depth? 2 meter. At the top, overburden pressure is 0. It increases linearly since overburden pressure is equal to the unit weight of soil into height. It is linear, right? It is in see this sigma is this is the gamma. Gamma means the unit weight of the soil. It is constant, and this z is the depth of the soil. It is increasing linearly. So see, this is increasing linearly. So at the top it is 0, and so at 2 meter depth, what is the unit weight of soil? It is the unit weight of soil above the groundwater table is 18. So here it is 18 into 2. So 18 into 2 over here, so that is 36 kilonewton per meter square. Okay. So now here is water table. Okay. So here there is water table. So let me just find out the overburden pressure at this depth, that is at the critical depth, which is at a depth of 6 meter from top of the soil. Okay. So overburden pressure at 6 meter, that is at critical depth. So what will be the overburden pressure at critical depth? That is 6 meter. So this part is dry, we know the, or maybe partially saturated, we know the unit weight of this part, which is 18. So sigma dash is equal to 18 into 2 plus this portion. What is the length of this portion? The total is 6. This whole portion is 6. This portion is 2. So that means this portion will be 4. So that means 4. And what will be the unit weight of this part? Since this is total submerged, we must use submerged unit weight of this part. So what is the submerged unit weight of this part? It is saturated unit weight minus the unit weight of water. So what is the saturated unit weight? It is, see, the unit weight of sand below the water table is 20 kilonewton per meter cube. Above the water table it is 18, and below the water table it is 20 kilonewton per meter cube. So can we write it like, so we can write it like this. So 20 minus 10, it is the submerged unit weight. If we solve this, we will get the unit weight at 6 meter depth. It will be 76 kilonewton per meter square. Okay, it will be like this. 7 here, the unit weight is 76 kilonewton per meter square, and we have just, it is at this depth. And I have just told earlier that below the critical depth we must consider that the overburden pressure is constant for solving such problems. Okay, so that means at the 15-meter depth, here it is 15-meter depth, the unit weight is also 76 kilonewton per meter square. So in what happens, what is happening over here is that the overburden pressure was increasing linearly up to 2 meter. Then afterwards, uh, uh, till the critical depth, we have found out the overburden pressure at the critical depth, that is at 6 meter. This part is totally submerged, and after that the whole overburden pressure is constant. So at the critical depth, overburden pressure is 76 kilonewton per meter square, and at the base of the pile it is also 76 kilonewton per meter square. Okay, so now let me just use all these things to find out the ultimate bearing capacity of the pile, which has been asked to find in the question. So K is equal to 2. In this question, the lateral earth pressure coefficient, it is mentioned, and delta is also mentioned over here, which is 3/4 of the frictional angle. Frictional angle is how much? Frictional angle is 40. So it is equal to 3/4 into 40 degrees. So that means phi is, this delta is equal to 30 degrees. This 10 into 3, 30. So delta is 30 degrees. So let me just now find out the unit screen friction resistance first along the length of the pile. So along the length of the pile, I will find out screen friction resistance. Okay. So what was the formula for screen friction resistance? It is K into sigma dash Fe, that is the average effective overburden pressure multiplied by tan of delta. Okay. So FS1, that is the unit screen friction resistance for this part, for the top part. Okay, above the groundwater table. The height, the depth of this part is 2 meter. Only the thickness of this part is 2 meter. So let me just write down the formula once. It is K sigma dash AV into tan delta. This is the formula for unit screen friction resistance, right? So FS1, that is the unit screen friction resistance for the top part. It will be, so K is equal to how much? K is equal to 2, and this tan delta, how much will be tan delta? Tan delta means tan of 30 degrees into average effective overburden pressure. So what will be the effective average overburden pressure at this height, at this depth, that is at a depth of 2 meter. So 36 kilonewton per meter square is the overburden pressure at this point at 2 meter depth. So what will be the average effective overburden pressure at the top? It is how much? It is 0 at the ground surface. So that means 0 plus 36 by 2. Hello.
Yes, it is.
Uh, have you understood what I am saying?
Yes, I got it.
Okay, okay. So that means it will be 0 plus 36 by 2. Okay. So if you calculate this, it comes out to be 20.8 kilonewton per meter square. So this one is screen friction resistance for the top part, that is along this part, or maybe along this part, that is above the part along the part above the groundwater table. So 0 to 2 meter. So this part is from 0 to 2 meter. Now for the second part, for this part, okay, up to critical depth, because beyond critical depth the overburden pressure is constant. We have considered it. So we must consider. So we must find out the distribution of the screen friction along this part. So we need to find out. So Fs2, this will be from 2 meter to 4 meter. No, sorry, 2 meter to 6 meter. Okay, the thickness is 4 meter. The thickness of this part is 4 meter, but this up from this point to this point the thickness is 2 meter, and from this point to this point the thickness is 4 meter, and the total is 6 meter. So screen friction resistance from 2 meter depth to 6 meter depth, right? From 2 meter depth to 6 meter depth, we must find out. So this one will be from 2 meter depth to 6 meter depth. It will be 2 into tan 30 degree, that is k into tan delta, it is constant, into effective overburden pressure, right? Effective average overburden pressure C. At this point, what is the overburden pressure? It is 36. And at this point, what is the overburden pressure? It is 76. So that means we need to take the average of 36 and 76, right? So here we will do it just that. So average of, so half means average of 36 plus 76. If we calculate this, we will get unit skin friction resistance along that part to be 64.7 kilonewton per meter square. Okay, and so now we know the unit screen friction resistance along this part. Now we have considered the effective overburden pressure below the critical depth to be constant. So what is the overburden pressure at the critical depth? That is at 6 meter. It is 76 kilonewton meter square. So we have considered that to be constant along the rest of the depth. So let me just write it down over here. So the screen friction resistance for the third part, that is from 6 meter depth to the 15 meter, that is up to this point. So from 6 meter depth to 15 meter depth. Okay, what is the unit screen friction resistance? 2 into tan 30 degree, 2 into tan of 30 degree into average of 76 and 76 kilonewton per meter square is the average, is the effective overburden pressure at the critical depth, and it is constant beyond that. So the what will be the average? Average will be 76 plus 76 divided by 2. That means 76. So if we calculate this, we will get F3 87.8 kilonewton per meter square. Okay. So now let me find out the total screen friction resistance. Till now we have found out the unit screen friction resistance. Okay. So now we will find out capital QF. Capital QF. What is capital QF? It is screen friction resistance. It is screen friction resistance along the surface of the pile multiplied by the surface area. So till now we have found out Fs1, Fs2 and Fs3. That is the screen friction resistance, unit screen friction resistance along three different segments of the pile. Okay. Now we will find out the total screen friction resistance. So it will be equal to, we can write it like this: Fs1 multiplied by surface area of that portion, Fs2 multiplied by surface area of that portion, and Fs3 multiplied by surface area of that portion. If we find out these three terms separately and sum it up, we will get the total screen friction resistance. Okay. So that means, what is the Fs1 in this case? Fs1 is 20.8. So 20.8 multiplied by, what is the surface area of this portion, of the top portion? We know the diameter, right? What is the diameter of the pile? The diameter is 0.3 meter or 300 millimeter. Okay. So what will be the surface area of the top portion? It is pi into d into the length of the section of the top portion. The length of the top portion is 2 meter. This length is 2 meter. So that means pi into d into 2. So d is 0.3. So that means Fs into pi into 0.3 pi into d into L. What is L? L is 2 meter. Okay. So plus F2 into, that is the Fs2, that is the unit screen friction resistance of the second portion. Okay, of the second portion multiplied by the surface area of the second portion. So what is the value of Fs2? Fs2, the value of Fs2 is 64.7. So 64.7. And what is the surface area of the second portion? It is also pi into d into L. So pi d is constant, pi into d is 0.3. But what is the length of the second portion? The length of this portion from 2 meter to the critical depth, that is 6 meter. It is 6 minus 2, that is 4 meter. So it is 4 meter. Plus plus Fs3, that is the last portion. For the last portion, Fs3 is how much? Fs3 is 87.8 kilonewton per meter square. Okay. And what is the surface area of the last portion? That is from 6 meter depth to the 15 meter depth. How much is the thickness? 15 minus 6. How much it is? It is 9, right? Yes, it is 9. So what will be the surface area of the last portion? It is pi into 0.3 into 9, right? If you calculate these three terms and sum it up, after that you add all these three terms and you will get, the answer will be 1028 kilonewton. This is the total screen friction resistance that the soil is providing, okay, along the length of the pipe. Total screen friction resistance. And now another part, that is the end bearing part. What will be the end bearing part? QB. So what will be the end bearing part? This is sand, right? This is a cohesionless soil. So what will be the end bearing part? QP equal to sigma dash NQ. So sigma dash NQ. So what is the overburden pressure at the tip of the pile over here? It is 76, right?
Next page, sir.
Huh?
Next sheet. Next sheet. What you are writing that currently? That is not appearing here.
It is not appearing. Wait a minute.
Next one. Last one.
Wait.
That you are doing 1028. That page.
this page, right?
Last page. Third
This
page.
one.
Last page.
This one. Have you understood this? Where I have
This
find.
I got it. I got it. I am understanding that.
Okay, you have understood. You have understood this, right? The total screen
I got
fix.
it.
Okay.
I got it.
Okay.
Okay, sir.
Now after that, I am finding out the end bearing resistance. Okay, the total end bearing resistance. So where was I? So we are finding out total end bearing resistance. So the overburden pressure at the tip of pile cap, that is at the base of the pile. And what is the overburden pressure? The overburden pressure is, we have considered that overburden pressure is constant after the critical depth. Beneath the critical depth, overburden pressure is constant. We have considered, so that overburden pressure is 76 kilonewton per meter square, right? So what is the formula we have derived for the for the unit end bearing capacity, for the unit end bearing resistance? So for unit end bearing resistance for cohesionless soil, it is sigma dash nq, this formula, sigma dash nq. So qb will be equal to q is equal to q u b into q u p into ab. This q u p is equal to sigma dash nq, right? Sigma dash nq. So this overburden pressure at the base of pile. Okay, overburden pressure at the base of the pile is how much? It is 76 kilonewton per meter square. The effective overburden pressure at the base of the pile is 76 kilonewton per meter square. That is sigma dash. And what is the value of nq? It is the bearing capacity factor. It is given in the question, I believe. See, it is nq is 135. NQ is 135. So NQ is 135. So we know all the things. So now AB, what is AB? AB is the area of the base of the pile. If we know the diameter, we can find out the AB. So how much is the diameter? Diameter is 0.3 meter. So what will be AB? AB is pi by 4 into d squared. That is pi by 4 into 0.3 square. So if you calculate this, you will get the value of AB. Now, if you multiply all these three things, you will get the value of QB. That is the total end bearing resistance. If you multiply all these three things, you will get the value of QB, which is equal to 1028. 10 1 minute. No, sorry, 1028. No, not 1028. It will be 725 kilonewton. And we must ensure that this QUP, that is sigma dash NQ, must be less than 11,000, right? Must be less than 11,000 kilonewton per meter square. I have written it over here. This QUP for cohesionless soil, QPU for cohesionless soil must be less than 11,000 kilonewton. So that means this sigma into NQ, sigma dash into NQ, that means 76 into 135 should be less than 11,000 kilonewton per meter square. If you multiply 76 with 135, it comes out to be 10260 kilonewton per meter square. Okay, it is less than 11,000. Now 10260 multiplied by this AB, this part, you will get QB, capital QB, this. If you multiply this with this, you will get QB, which is 725 kilonewton. So now the total bearing capacity of pile, that is the QF plus QB, that is total screen friction resistance plus total end bearing resistance. If we just sum it up, we will get the ultimate bearing capacity of pile. So what is the value of QF? QF is 1028, which you have already found out. 1028 plus QB, what is the value of end bearing resistance of pile? End bearing resistance of pile we have also found out, it is 725. So plus 725 kilonewton. Now if we just have to sum it up together, so it is 1753 kilonewton. So this is the total, and this is the total bearing capacity of ultimate bearing capacity of pile. We have been asked to find out this value only. See, ultimate load carrying capacity of pile. That is the ultimate bearing capacity of the pile. Please let me know if you have any problem, if you have any doubt in this question. Please let me know if you have understood or not. If you have any doubt, please let me know, or else I'll proceed to the next
Previous,
question. Yes.
previous slide.
Okay. Okay. Which slide? Have you understood this problem?
Just previous slide, sir. Just.
Oh, this one.
Yes, sir. What is that QB is equal to QUP, we write it as, or PU we write it?
Oh, okay. 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 This one is yes. Yes. Yes.
That is PU.
Yes. That is PU. This one is PU.
Okay, okay. That's why I was having that doubt.
Okay. 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 QP.
Okay, sir.
Okay.
Now it's okay.
Okay. Okay. Thank you. Thank you.
Okay, sir.
So now let's come to the second problem. So what is the second problem? So estimate the safe load carrying capacity. Safe load. When you encounter such term, safe load, you must incorporate the factor of safety. We must incorporate factor of safety to the ultimate bearing capacity. Okay, you just need to incorporate that factor of safety when you find such term, safe load. So estimate the safe load carrying capacity of a single boat pile of 25-meter long and 500 millimeter diameter. The factor of safety is 2.5. The strength of different soil layers is as follows. Okay, so we need to find out the safe load carrying capacity of a boat pile. So what is the length of the pile? Length of the pile is 25-meter, and the diameter of the pile, what is the diameter? Diameter is 500 millimeter, that means 0.5 meter. Factor of safety is given 2.5, and all the data are given over here. Along the depth, undent shear strength of the soil is given, and also the adhesion factor is given. Okay, that is alpha is given. So we need to estimate the safe load. Okay, so for estimating the safe load, we must find out the ultimate load that the soil can, that the pile can carry. That is the ultimate load. That is the ultimate load which the soil can carry. So after finding out the ultimate load, ultimate bearing load, if we just divide it, divide it by the factor of safety, the ultimate load divided by factor of safety, we will find out, we will get the safe load. Okay, so that means we need to find out QU. After finding out QU, we will divide QU with the factor of safety. After dividing QU with factor of safety, we will get the safe load. So let us just solve. Let me just solve the problem. So first of all, we need to find out QU. So what is QU? QU is equal to QB plus QF. So QU, capital Q is equal to capital QF plus Q into B. We need to find both this term, that is the total end bearing resistance and total skin friction resistance. We need to find these two terms. After that, we need to sum it up. After summing it up, we will get the value of QU, that is the ultimate load. And after getting the ultimate load, we will divide that by factor of safety. After dividing that, we will get the value of safe load. Okay, so let's get started. So QF, what is QF? So QF is capital QF is equal to Fs into As, that is the unit skin friction resistance multiplied by the surface area of the pile. So Fs into As. So how much is the Fs? So we need to find out Fs. So we have this undent shear strength. Okay, so undent shear strength, and see, this one is clay. Okay, this one is clay. This one is clay, and undent shear strength. Undent shear strength means this one, this, all these values are also cohesion values. Okay, see, these values are also C. Okay, and so let me just solve it. So QF is equal to Fs into As. Let me just check the formula for the cohesive soil. Formula of Fs, that is alpha into C dash. Alpha into C dash is the formula for Fs, that is the unit screen friction resistance, and QPU, that is the unit end bearing resistance, it is 9 into C. This C is the cohesion at the base of the pile, and this C is along the length of the pile. Okay, so let me just show you how to do this. So Fs into As. So we have so here along the depth, along the 0.5, 5 to 10, 10 to 20, 20 to 30, all the data are given. Okay, and the length of the pile is 25 meter. Fine. So length of the pile is 25 meter and up to 30 meter, all the data are given. So let me just write it like this. So Fs, let me just draw it once. So 0 to 5, 5 to 10, 10 to 20, 20 to 30. Okay, but the length of the pile is 25 meter. So we are dividing the pile into segments. Up to 30 meter, the data are given. Up to 30 meter, informations are available, and the length of the pile is 25 meter. So we are dividing it into the zones that are given in the question: 5, 0 to 5, 5 to 10, 10 to 20, 20 to 30. So 0 to 5, 5 to 10, 10 to 20, 20, 20. This one is 30. How much it is? It is, sorry, it is up to 30. It is given, but the length of the pile is 25 meter. So that means this one will be 25. The last depth will be 25. So the thickness, this thickness is 5 meter. This thickness also 5. This thickness is 10, and this thickness is 5. The thickness of this portion is 5. Thickness of this portion is also 5 meter. Thickness of this portion is 10 meter. Thickness of the last portion is 5 meter. Okay, so Fs. So we will find out the screen friction resistance along all this, along these segments. Okay, along the surface of these segments. So Fs of the first segment, that is Fs1. So what is the value of Fs1? It is alpha into C, right? So alpha of the first segment is 1. Alpha into C, what is C? C is 25. So that means Fs is 25. 25, right? Alpha into C. And what is the value of As of the first portion? First portion Fs is pi into d into L. So what is L over here? It is 5. So pi into, what is the diameter of the pile? It is 0.5 meter. So pi into d into L. How much is L? It is 5. This is the Fs1. So after that, if so this one is up to this one is Fs1. The Fs1 is sorry, Fs1 is this alpha into C. This one is As1. Okay, As1. So this one is Fs1, that is alpha into C. Alpha is 1. Alpha is 1 for the top part, and C is 25. So this one is Fs1, and this one is As1. Okay, so now Fs2 into As2. So what is the Fs2 for the second part? For the second part, Fs2 is alpha into 38. Okay, alpha into 38. So alpha into 38. Alpha for the second portion is 1, and C is 38. So alpha into C is 38. So 38, this is the Fs2 multiplied by the surface area of this segment from 5 meter to 10 meter, how much it is? It is pi into d, that is 0.5 meter, into the thickness of this segment, that is 5 meter from 5 to 10 meter depth. Okay, this one is as1, this one is this one is as2, this one is fs2. Okay, so now we must find out the unit stream friction resistance of this part. Okay, and also the surface area of this part from 10 meter to 20 meter depth. The thickness is 10 meter. So fs3 into as3, how much is fs3 into as3? fs3 is alpha into c. Here alpha is 0.8 and c is 50. So 0.8 into 50. So 0.8 into 50 is alpha c, that is the fs3, into what is the as3, that is the area of the third segment, surface area of the third segment. So that is pi into d into L. D is 0.3 and length is 10 meter. So pi into 0.5, right? How much it is? It is 0.5, sorry. 0.5. So 0.5 into 5 meter. This one is AS3. That is the, oh no, the length is how much? The thickness of third portion from 10 meter to 20 meter. It is 10 meter. So that means it will be 10. Pi into D, that is 0.5 meter, into L. So this one is fs3 into as3. After that, we need to find out the screen friction along the last portion, that is the fourth portion, that is from 20 meter depth to 25 meter depth. So fs4 and as4 we need to find out. How much is fs4? fs4 means alpha into c. How much is alpha for the fourth portion? It is 0.4 and 100. So alpha into c means how much it is? Alpha is 0.4 and c is 100. So this one is fs4 multiplied by the surface area of this portion. How much is the surface area of this portion? The thickness is 5 meter from 20 meter depth to 25 meter depth. The length is, the thickness is 5 meter. So that means it is pi into 0.5, that is pi into d into 5 meter. This is the as4. Now if you just solve all this part, wait a minute please. Now if you just solve all the part and sum it up, you will get the value of QF, that is the total screen friction resistance. Please wait a minute, I'm resharing my screen. Hello, can you see my screen? Please let me know if you can see my screen. Hello, please let me know if you can see my screen or not.
Your is okay, sir.
Hello?
Now it is okay, sir.
Okay. So where was I? Yes, the area of the fourth portion, the surface area of the fourth portion, that is pi into d into 5 meter, the thickness of the fourth portion. So pi into d into 5 meter. This is the area of the fourth portion. After, now if you just solve all these things, all these equations, and if you just sum it up, you will get the value of QF, capital QF, that is the total screen friction resistance. So QF you will get, QF will be equal to, QF is equal to 1437 kilonewton. Okay, Now we have found out the value of QF. Now we need to find out the value of total end bearing resistance. Okay, total value. What is that? We need to find out the value of total end bearing resistance, that is QB. So we need to now find out the value of QB. So what is QB? So QB for cohesive soil, what is it? C. For cohesive soil, QB is equal to small QPU into area of the base of the pile, right? So QPU is equal to CNC is equal to 9C. So 9C into area of the base of the pile. So that means we can write it like this: QB is equal to QPU into AB, which is equal to 9C into AB, area of the base of the pile. This C corresponds to the cohesion of the soil below the base of the pile. So what is the cohesion of the soil below the base of the pile? The pile length is 25 meter and up to C, up to 30 meter data is given. So this is the cohesion of the portion of soil below the base of the pile, below the pile tip. C is equal to 100. Okay, so C is equal to 100 below the base of the pile. Cohesion of soil below the base of the pile, it is 100. So that means QB, capital QB will be equal to, if we write it like this, 9 into 100 into B. What is the area of the cross section of the pile? Area of the base of the pile, diameter is 0.5 meters. So that means pi by 4 into 0.5 square. If you just calculate this, you will get QB. If you just calculate this, QB will come out to be 177 kilonewton. Okay, so that means QU, that is the ultimate load. What is the ultimate load that the pile can carry? It is capital QF, that is the total screen friction resistance, plus QB, that is the total end bearing resistance. How much it is? What is the value of QF? QF is 1437. So QF is equal to 1437 plus QB. What is QB? QB is 177. So if you now you just need to sum it up. So after summing these two values, you will get QU to be equal to 1614 kilonewton. Now here we have been asked to find out, in this question we have been asked to find out the safe load. What is the safe load? If the factor of safety is 2.5, we just need to divide the ultimate load by 2.5. So that means safe load is equal to QU divided by factor of safety. That means 1614 divided by 2.5, and this one is equal to 645.6 kilonewton. Okay, this one is the answer. So if you have any problem, if you have any doubt in this question, please let me know, or I will proceed to the next question. Please let me know if you have any doubts.
You can proceed, sir.
Okay. So this one is the third question. So what is the third question? Third question is, a concrete pile is given. A concrete pile. Here the pile is concrete and this is a square cross section. The pile is not circular. It is square in shape. Okay, square pile. So the dimension is given. Dimension is 30 millimeter by 30 millimeter. That is the side of the square. The side of the square is 305 millimeter, driven to a depth of 20 meter. That means we know the length of the pile. Length of the pile is 20 meter below the ground surface in a saturated clay soil. A summary of variation of frictional resistance FC, that is Fs, obviously frictional resistance, obtained from a cone penetration test. Okay, so the unit screen friction resistance is obtained from the cone penetration test. From cone penetration test, remember one thing, from cone penetration test we can get QB as well as QB means small q pu. That means the unit end bearing resistance. From cone penetration test, we can get unit end bearing resistance, that is small qppu, as well as we can get the frictional resistance. Okay, we can get all these values from the cone penetration test. So we have been asked to estimate the frictional resistance of the pipe, the frictional resistance that the soil is providing to the pipe. Okay, so let me just solve the problem. So along the depth, frictional resistance is given over here, and it is given in kg per centimeter square. So we just need to convert it into kilometer per meter square. So FC, how much is FC from, let me just write it down over here. Depth FC, how much it is? 0 from 0 to 6 meter depth, it is 0.35 kg per centimeter square. From 6 to 12, it is 0.56. From 12 to 20, it is 0.72. We just need to convert it into kilonewton per meter square. So FC into kilonewton, FC in kilonewton per meter square. This FC is also equal to Fs. Remember this. FC is same as Fs. So if we just convert this into kilonewton per meter square, we will get 0.35 will be 34.34 kilonewton per meter square. 0.56 will be 54.94, and 0.72 will be 70.63. I hope you know how to convert this frictional resistance from kg per centimeter square to kilometer per meter square. So after this one is FC in kilonewton per meter square. Okay. So here is a graph. Here is a graph. From this graph, we need to find out the adhesion factor. Okay. We need to find out the adhesion. This one is for cone penetration test only, this curve. The curve, here the curve is given in the question. We need to find out the adhesion factor for the pile along the segment. So here also a 20-meter pile is divided into 3 segments, 0 to 6, 6 to 12, and 12 to 20. Let me just draw it. Let me draw it over here. Over here. So along the depth, frictional resistance is given 0 to 6, 6 to 12, 12 to 20. So 0 to 6 meter depth, from 6 to 12, 12 to 20. That means the thickness is this portion, the thickness of this portion is 6 meter. Thickness of this portion is also 6 meter. The thickness of the last portion is 8 meter. Okay. So here we need to find out the adhesion factors, right? We need to find out the adhesion factors. So how we will find out the adhesion factor? We need to find out FC by PA. FC by P. What is FC? FC is the frictional resistance, unit frictional resistance, pin friction resistance. And what is PA? PA is the atmospheric pressure. Okay. PA is the atmospheric pressure. It is used for a reference over here. So PA for reference, we consider it, generally we consider it to be 100 kilonewton per meter square. Okay. So FC, we need to find out the adhesion factors for all these 3 segments. Okay. For all the 3 segments, we need to find out the adhesion factors at alpha dash for cone penetration test. So alpha dash for the first segment. So what is the FC for the first one? So FC for the first segment is 34.4, right? So FC1 is 34.4 and PA is equal to 100 kPa. all this in kilonewton per meter square. This is also in kPa. Also in kPa. So what will be FC1 by PA? FC1 by PA is 0.34, right? 0.34. So 0.34 will be somewhere over here. So 0.34 will be somewhere over here, and this is a concrete pile. It is given in the question. If we just draw a line like this, and if we just draw a line over here on this axis, on y-axis, we will get the value of alpha dash. So for FC1, for the first segment, where FC1 by PA is equal to 0.34, alpha dash 1 is equal to, from the curve we get 0.84. Alpha dash over here, the value is around 0.84. Similarly, for the rest two segments, we must find out. For the next segment, FC2 is 54.94. So FC2 divided by PA, that means 54.94 divided by 100. So it will be 0.54. So 0.54 will be somewhere over here, So 0.54, we draw a line like this and extend it over here. We'll get the value of alpha dash around 0.71. So alpha dash 2 will be 0.71. Okay, similarly for the third segment, where FC3 is 0.72, so 0.72 divided by PA, that is 100, FC3 by PA will be equal to 0. No, so yes, 70.63 here, 70.63. FC3 is 70.63 and 70.63 kilonewton per meter square, and PA is equal to 100 kilonewton per meter square, 100 kilonewton per meter square. So FC3 by PA will be equal to 0.70, around 0.70. So 0.70 will be somewhere over here, So if we just extend this line like this and extend this line over here, we will get the value of alpha dash 3. So alpha dash 3 lies around 0.63. It will be around 0.63. Okay. So we now have the value of adhesion factors of all the three segments. So now we can find out the unit screen friction resistance, that is alpha into C. Yes. So yes. So this one is the resistance. So we need to what we need to do is that instead of C, we need to multiply that alpha dash. That one is alpha, this one is alpha dash. We need to multiply this alpha dash with the unit screen friction resistance, that is with all these FC values. Since we get all this value from cone penetration test. Okay, so what we need to do is that we need to multiply respective alphas with FCs, with the value of FC. This one is FC1, this one is FC2, and this one is FC3. We need to multiply the adhesion factors with this, and also we need to multiply the surface area along the three segments. So what we need to do is that we need to multiply the adhesion factors with the respective frictional resistance, and we need to also multiply that thing with the surface area of that segment. And we need to do it 3 times for all the three segments. After finding out for the three segments, we need to sum it up. So let me just do it over here. So QF is alpha into FC into AS. Okay, alpha into FC into AS, summation of alpha into FC into AS. So for the first part, alpha 1, FC1, AS1, how much it is? Alpha 1 is how much? Alpha 1 is 0.84. So 0.84. into how much is the value of FC1? FC1 is 34.34. FC1 is 34.34. And how much is AS1? How much is AS1? It is the perimeter multiplied by the length of that segment. Since this is a square pile,
Square
this is
pile.
the square pile, how much will be the perimeter? How much is the perimeter? It is 4 into A, that is 0.305 into 4. So it is the perimeter will be around 0.305 into 4. And how much is the length of the segment? What is the length of the segment? The length of the segment is 6 meter.
6 meters.
Yes, 6 meter. So 6. This is the value of alpha 1, FC1, AS1. Similarly, we need to find out for alpha 2, FC2, AS2. So what is the value of alpha 2? Alpha 2 is around 0.71. And what is the value of FC2? FC2 is 54.94. 54.94. And what is the value of AS2? AS2 is perimeter into length. Perimeter is how much? 4 into 0.305 into length of the third segment is how much? It is 6 meter. Similar area. And after that, we need to find out the screen friction resistance for the third segment, that is alpha 3, FC3, AS3. Okay. So how much is alpha 3? Alpha 3 dash, actually all these are alpha dashes. So how much is alpha 3 dash? Alpha 3 dash is equal to 0.63. How much is FC3? FC3 is 70.63. 70.63. And what is the perimeter? Perimeter is 4 into 0.305 meter. And what is the length of the third segment? Length of the third segment is 8 meter. Now 8 meter. Now if you just calculate all the three terms and sum and add all the three terms after multiplying, you will get the value, that is sigma, that is the summation of alpha dash FC into AS after multiplying all the terms. And after multiplying the terms, we need to just sum it up. So after summing it up, we will get the value. We will get this one is QF, that is the total screen friction resistance. This one will be equal to 931 kilonewton. Okay, 931 kilonewton. So if you have any problem in this question, please let me know. We have been asked to find out the total screen friction resistance only. So if you have any doubt, please let me know.
It's okay, sir.
Okay, one thing, let me add. We know that is the screen friction resistance. What is it? Screen friction resistance, like we used to write earlier, it is AS into FS, right? FS is the unit screen friction resistance and AS is the surface area of the pile. AS into FS. So this AS into FS for cohesive soil, we can write it like this: AS into alpha into C dash, that is the alpha is the adhesion factor and C dash is the cohesion along the length of the pile. So this FS, if you perform, if you perform cone penetration test, from that if you get the value of from that cone penetration test, you get the value of cone tip resistance and the frictional resistance. So frictional resistance is represented by FC. Actually this FS, we can this, so what is this FS? FS is the unit screen friction resistance. FS is alpha into C dash. This one is FS. Okay. So the value of frictional resistance that you get from cone penetration test, that is FC, the resistance of that, it can be written like this: alpha dash FC. Similar thing that we did over here, that we have done over here, alpha dash into C. alpha dash into fc is equal to actually fs. Okay, alpha into c dash is similar to that of alpha dash into fc. That is why we are multiplying. We multiplied everything that addition factors with fc. So fs, that is the unit screen friction resistance for this problem, is equal to alpha dash into fc. That is why we did this. We multiplied alpha into fc1 to find out fs, and fs into as gives qf, that is the screen friction resistance. So I hope you have understood this.
Yes, sir.
Okay. So now let me proceed to the third question. No, sorry, fourth question. So what is the fourth question? A concrete pile of 45 centimeter dia. So a concrete pile of 45 centimeter diameter is 45 centimeter, that is 0.45 meter, was driven into sand of loose to medium density to a depth of 15 meter. So that means the length of the pile is 15 meter. And all the informations are given over here. The average unit weight of soil along the length of the pile is given. It is 17.5 kilonewton per meter cube. Average phi is also given, which is 30 degrees. Average Ks value, that is the average lateral earth pressure coefficient, is also given. It is 1. And delta, that is the angle of friction between the soil and the pile. It is 0.75 of phi. It is given. We need to find out the ultimate bearing capacity of the pile and also the allowable load. So that means we need to find out the ultimate load and divide that by using factor of safety, which is 2.5. So after that we will get the safe load or the allowable load. Both are same. So water table is at a great depth. We need to use Beres-Ansatz method. Okay, so this is a similar method. We have been doing that only. So let me just solve the problem. So just let me draw it once. Let me draw the pile once. Let me draw it over here. This is a graph. Using this graph, we need to find out the value of NQ. Okay, find out the value of NQ. So let me just draw the pile. So length of the pile is 15 meter and diameter is 0.45 meter. So this is a 15 meter pile. The pile is 15 meter. What is the unit weight? Unit weight is 17.5 kilonewton per meter cube. Unit weight is 17.5 kilonewton per meter cube. How much is phi? Phi is 30 degrees. Phi is 30 degrees. Case is 1. Case is equal to 1. And delta is equal to 0.75 of phi. Delta is equal to 0.75 of phi. Okay, so 7.5, so 0.75 into 30 degrees, and which is equal to 22.5. So now let me just solve the problem. What we need to find out? We need to find out the ultimate load, and after that we need to use the factor of safety to find out the safe load. So what is the value of QU? This is sand. So QU is equal to QB plus QF. So ultimate load is equal to the end bearing total end bearing resistance plus the total screen friction resistance. Okay, so QB, how much is QB? QB at the base of the pile, how much it is? It is, let me just go to the formula. Yes, for cohesionless soil, it is sigma dash into NQ, right? Sigma dash into NQ QPU. So QB is equal to sigma dash into NQ into AB plus what is QF? QF is equal to how much it is? What is the formula for QF? The formula for QF is equal to Fs into surface area AS, Fs into AS, which is equal to K into sigma AV dash into tan delta. So QF is equal to surface area into QAV dash into K into tan delta, right? So we need to use this to find out the ultimate load carrying capacity. Fine. So in first of all, let us find out the value of sigma dash. Okay, let me do it separately for better understanding. So what is the value of sigma dash at this portion? At this portion, at the base of the pile, because we are finding out sigma dash for bearing capacity for the end bearing. We are finding out sigma dash for the end bearing. Okay, so for the end bearing we must consider sigma dash overburden effective overburden pressure at the base of the pile. So what is the overburden pressure at the base of the pile? Effective overburden pressure, it is 15 into 17.5. So sigma dash is equal to 15 into 17.5, right? So 15 into 17.5 comes out to be 262.5 kilonewton per meter square. Fine. And now let us find out sigma AV dash. Sigma AV dash. See what is happening over here. At the top, overburden pressure is 0. At the top, overburden pressure is 0, and it is increasing linearly because our effective overburden pressure is equal to sigma into z. Z is the depth, and at a depth of 15 meter, how much is the effective overburden pressure? It is 262.5. So here it is 262.5. So what is the average? 0 plus 262.5 by 2. We have done like this in the earlier problem. So Q average, that is sigma average, sigma effective average is effective average overburden pressure is 20 plus 262.5 by 2, and this comes out to be 131.25. Half of this, half of 262.5, 131.25 kilonewton per meter square. Okay. Now we need to find out the value of AB and AS. AB and AS. What is the value of AB? What is the value of AB? What is the area? Area. What is the diameter of the pipe? Diameter is 45 centimeter. That is 0.45 meter. So what will be the area of the base of the pile? It will be 0.4 into 0.45 square. So this one comes out to be 0.159 meter square, right? AB. And what is the surface area? That is AS. How much is AS? How much is AS? We that is perimeter into length. How much is the perimeter? It is a circular pile, right? It is a circular pile. It is a circular pile because diameter is given, so it is a circular pile. So what is the perimeter? It is circumference, that is pi d. So perimeter into the length of the pile, that is pi into d into L. So that means AS is equal to pi into d into L, right? So what is pi? Pi into d. What is the d? D is 0.45 meter, 0.45. And what is the length of the pile? Length of the pile is 15 meter, 15 meter. And this comes out to be 21.195 meter square, the surface area of the pile. Okay. So surface area of the pile. So now we have everything. See, we have no. We have sigma dash. We have AB. We have AS sigma AV dash. We have the value of K. We also have tan delta. We know the value of delta, so that we can, and easily we can find out the value of tan delta. So we don't know the value of NQ, the bearing capacity factor. Okay, we don't know the value of NQ. So how we will find out the value of NQ? So for finding out the value of NQ, we need to use this chart. Okay, we need to use this chart to find out the value of NQ. So what is phi? Phi is 30 degrees. Average phi is 30 degrees. And we need to find out, see, average phi, this phi is 30 degrees, and all the curves, see, are given in terms of L by D. So we need to find out L by D ratio. So L by D ratio, what is the L by D ratio of the pile? Length is how much? It is 15 meter. And what is the diameter of the pile? It is 0.45 meter. So 0.45. How much? So how much is L by D? L by D is 33.3. Okay. So L by D is 33.3. So now for phi equal to 30 degrees and for L by D is equal to 33.3, the curve will lie somewhere over here. So if we just extend that point onto the y-axis, we will get the value of NQ. So value of NQ will be around 16.5. So value of NQ, so value of NQ for L by D is equal to 33.3 and phi equal to 30 degrees. NQ will be equal to 16.5. So now see, we have the value of all the parameters. We know the value of sigma dash. We know the value of NQ. We have just found out from the graph value of NQ. We know the value of AB, that is the area of the base of the pile, AB. We know the value of AS, that is the surface area of the pile. We know the value of sigma average, that is the average effective overburden pressure at the pile depth, at the base level of the pile. We know it, average one. K is the lateral earth pressure coefficient. It is also given. It is 1. And tan delta. Delta is also given. Delta is 22.5 degrees. So if we just put the values of all the parameters into this equation and solve it, we will get the value of total ultimate load. So after calculating, QU will be equal to, so after calculating, QU comes out to be, well, yes. So after calculating, this part is QB, that is the end bearing resistance, and this part is QF, that is the screen friction resistance. So after putting all the values of all the parameters into this equation, so after solving, you get the value of total ultimate bearing capacity of the pile, which is QU, that is the ultimate load. It comes out to be 1841 kilonewton. Okay, this is the ultimate load. And you have also been asked to find out the allowable load. Okay, see, we have been asked to find out the ultimate bearing capacity of the pile as well as the allowable load. Factor of safety is given, which is 2.5. So we just need to divide for Q allowable or the safe load. We just need to divide QU by factor of safety. So Q is 1841 divided by 1841 divided by factor of safety divided by factor of safety, that is 2.5. If you calculate this, it comes out to be 736 kilonewton. So this is the allowable load and this one is the ultimate load that the pile can carry. So these two are the answers of this question. So if you have any problem regarding this question, please let me know. Or else I'll proceed to the next question.
Okay, sir.
Okay. So the next question. Assume in question number 4, that is the previous question, that is this question only. We have been asked to assume that the water table is at the ground surface. Saturated unit weight is given. All the other data remain the same. We need to calculate ultimate load, ultimate pile, ultimate load, and also the allowable load. Okay, that means ultimate bearing capacity and the allowable load. We need to find out. So here, what is happening? We need to refer to question number 4, and in this case the water table is at the ground surface. That means this one is a diagram for question number 4. Here the water table was at a great depth. Assume the water table is at a great depth, and here the water table is at the surface. Okay, at the surface. So let me draw it. So 15 meter, the pile length is 15 meter, and the water table is at the ground surface. So gamma sat, that is the saturated unit weight is given, it is 18 kilonewton per meter cube. We need to find out QU, that is the ultimate load and the allowable load. So all the other data are same. So pile dia is 45 centimeter. So dia is 0.45 meter. K is equal to 1. That is the lateral earth pressure coefficient is 1. Delta, that is the frictional angle between the soil and the pile. It is also same, it is 0.755. 0.755, phi is 30 degrees. So this one will be around 22.5 degrees. We calculated it over here, 22.5 degree. So this one is 22.5 degrees. So we need to find out QU and QA. So let me write down the equation. QU is equal to QB plus QF. So QB is equal to sigma dash NQ into AB for cohesive soil. For sand. This one is sand, right? Yes, sand. So QF, what is QF? QF is Fs into As. What is Fs? Fs is sigma AV dash, that is the average effective overburden pressure, into K into tan delta into As. So this one is QPU, this one is Fs. So what is sigma dash? This one is for end bearing resistance, this one it is for screen friction resistance. So what is sigma dash? Sigma dash is the effective overburden pressure at the base of the pile. So what will be the effective overburden pressure at the base of the pile? Over here, gamma, this one is totally submerged because the pile is below the water table. Pile is totally submerged. So that means submerged unit weight into 15. So sigma dash is equal to submerged unit weight into 15. So how much is submerged unit weight? Submerged unit weight is, how much is the saturated? It is 18. Sorry, it is actually 18.5. So it is 18.5. So gamma submerged is 18.5 minus unit weight of water 9.81 into 15, right, the length of the pile. So it comes out to be 8.69 kilonewton per meter square. Okay, sorry, no, not this one. It comes out to be, if we calculate this, 18.5 minus 9.81 into 15, this one is 8.69. So 8.69 into 15, it comes out to be 130.35 kilonewton per meter square. Okay, sigma dash. And what is the value of sigma dash AV? Sigma dash AV, similar case, it is increasing linearly at the base of the pile. Effective overburden pressure is 130.35. Effective overburden pressure is 130.35. So that means the average effective overburden pressure will be 0 plus 130.35 by 2. It comes out to be 65.15, 65.18 kilonewton per meter square, right? So now if you just substitute the values of all the parameters into this equation, you will get the answer. You see, sigma dash we have found out, sigma AV we have also found out. We know the value of K, we know the value of tan delta. AS, what is the value of AS? The pile is similar, or the pile is similar to that of the previous question. We have calculated the value of AS in that question, in the previous question. So AS is how much? AS is perimeter into length. Perimeter into length. How much is the perimeter? What is the uh, dia of the pile? Dia is, I think, 45 centimeter. That means perimeter is pi into d 0.45 into L. How much is length? How much is the length of the pile? It is 15 meter. So this one is the surface area of the pile. So you know the surface area of the pile. You know the AB. What is the AB? AB is the area of the base of the pile. So AB is pi by 4 into d square. How much is d? It is 0.45 meter. So if you calculate these two terms, and you know sigma dash, you know AB, you know sigma dash AV, you know K, you know tan delta, and also A. So you just need to find out NQ. So from that graph only, because NQ depends upon only phi, and L by D. L by D is also same. L by D is how much? L is 15. L is 15, and D is how much? D is around 0.45. D is 0.45 meter. So L by D is 33.3, and phi is 30 degree. For 33.3 L by D ratio and phi equal to 30 degree, this bearing capacity factor NQ is equal to 16.5. So you also know the value of NQ, right? You also know the value of NQ. So if you just incorporate the values of all the parameters into this equation and calculate, you will get the value of QU. So after calculating, QU comes out to be, that is the ultimate load, it comes out to be 914 kilonewton. And if you just divide this by the factor of safety, QU by factor of safety, you will get the value of Q allowable. So how much is the factor of safety? The factor of safety is similar to that of the first question. It is 2.5. So that is 900, Q is 914. So 914 divided 2.5 is how much? It comes out to be around 366 kilonewton. So this is the allowable load. So this one is the ultimate load, and this one is the allowable load. So if you have any problem in this question, please let me know. If you have any doubts.
It's okay, sir.
Okay, so that is all for today. I will discuss the rest of the problem, all the other problems in the next session. Okay, so thank you for attending today's session.
Thank you, sir.
Okay, so goodbye and all the best.
Okay, sir. Thank you, sir.
Okay, okay. You may quit. You may quit the meeting now.